Hello, I would like you to introduce to the features that are added by the Mastodon Deep Lineage plugin, release 0.0.1, to the actual Mastodon plugin, the large-scale tracking and track editing framework for large multi-view images for Fiji. First of all, there are some numerical features added to Mastodon that can be computed via the feature computer. These are some spot features and some BranchSpot features, but I will not go into very much detail here, as they are quite well described in the README of the Deep Lineage plugin. But instead, I will talk in more detail about the new plugin lineage tree classification, since I think it covers quite some concepts and it's worth explaining then so that you know how they work under the hood, so that you can decide if it makes sense for your use cases to actually apply them. And secondly, there's the labeled image exporter that I will explain as well. But let's start with the lineage tree classification plugin. And for that, I have prepared an example dataset. The example dataset you find in the repository, and you will find a link to it also in the description of the video. In order to use that example dataset, you can go to Mastodon. This opens the Mastodon launcher. Then you go to Mastodon projects. I already have this in the list of my previously or recent projects. If you download the project to your machine, you won't have it in the list of your recent project, but then you just go to open another project and open the file from the file system. So I will open it directly from here. And this example dataset that I use to exemplify the classification of the lineage trees does not contain any image data. That's right, this dialog pops up. You can here just select open with dummy images, and then you get this view. This view shows you the big data view. So as you can see in the big data viewer, there's no images, just pure black background, but you can see some spots and you can also see them over time. And I have opened two other images. One is the track scheme, and that's this one, and this is the track scheme branch view. The difference between the two is that the track scheme shows the individual spots. And if you couple these windows, you can also, if you click here, you get the spots shown here in the big data viewer as well. And in the track scheme branch viewer, you don't see those individual spots, but they are, as you can see here, all those 10 to 15 to 20 spots that you see here, they are represented by this one line here that goes from time point 8 to time point 30. Yeah, what is the lineage classification plugin about? The lineage classification plugin is about, as you can see here in this example dataset, I have created some artificial lineages by tracking some artificial spots. And as you can see, the patterns that are reflected by these lineages, they are, some of them are a bit similar to each other, and some of them are also different to each other. So for example, this one here, I called it asymmetric 1 and asymmetric 2. They look quite similarish to each other. So there are some differences. So as you can see here, there's a further splitting event, which does not exist here, and also here is another splitting event, which does not exist here. But in general, these look similar to each other. And also, for example, these symmetric ones that I call symmetric 1, 2, and 3, they are also quite similar to each other. So the splitting events of the spots, they happen at different time points, but in all cases, there is splits into two spots. The root spot splits into two spots, which again split into other new spots. And then there's these ones that are called single division. So that's a spot which only divides once. And then there's this non-dividing. So it would make sense to, if you only look at these three, to maybe make up 4 groups. So This is one group, the symmetric ones, one group, the single division ones, one group, the non-dividing one, and one tree could be the asymmetric one. And exactly this you can achieve in an automatic way with the classification of lineage trees. So you can activate this plugin by clicking on plugins in every of these windows, classification of lineage trees, and then a new dialog opens up. And you have quite some parameters to enter there. One parameter is the crop criterion. So what you can do, you can decide, you have here these 30 time points, or you can see them here as well. And you can decide from which to which time point you want to do, you want to compute this classification. My case, I decided to start at the very beginning, so time point 0, and go to the very end, which is in this example time point 30. So this covers the whole data set, but sometimes it makes sense to, if you have a data set where you only tracked some of the lineages to further time points and you want to restrict the analysis to a time point which covers the time where all the tracks have been tracked completely, then it makes sense to set a different threshold here. An alternative criterion that you can select, and that would not be the time point, but the number of cells. And then you would select a starting number of cells and number of cells. That would mean, so for example here, time point 0, we have 8 spots already, and that gets more over time, and at the end we have 31 spots. So the whole data set would be covered if we would enter here 8 to 31. And then it would automatically select the time points where for the first time there is 8 spots and where for the first time there's 31 spots. So that's automatically converted into a time point. But for this example, I will stay with the time points. So from 0 to 30. And as I said before, or the next parameter is the number of classes that you can enter. And as I said before, I'm visually seeing here 4 types of lineages. So I expect or would like to let the lineage classification classify this whole data set into 4 classes. The next parameter, you can say the minimum number of divisions of lineages that should be included into analysis. If I would set this to 1, then, for example, this one, the non-dividing one, that would not be included in the analysis. So for some analysis, it might make sense to exclude these maybe, not so interesting from a terms of a lineage tree. Lineages, since they are not dividing at all. But for the example now, I will leave it in, so I will set the parameter to 0. The other 2 or 3 parameters I will explain in a minute, but let's first of all see how the result looks like of this. There's a box that you can tick on that you can show the dendrogram of the clustering. Okay, let's do this. And as you can see here, this is the result. And the result of this clustering of the lineage tree, of this lineage tree classification, is that we get 4 different classes. They are marked in 4 different colors. And as you can see, as we expected, the symmetric ones, the asymmetric ones, the single division trees, and also the non-dividing trees, they are grouped into distinct classes. Within Mastodon, also a text set is now created, and you can use this text set to color the lineage trees now. It's possible in both views. It's even possible in the big data viewer, so you can visualize it here as well. And you can see that by this, the division pattern of the lineage trees, or the lineage trees are grouped into classes that show similar division patterns. Now I would like to explain how this works under the hood a bit. And for this, I will show some slides. So in Mastodon, there exists the so-called spot graph and the BranchSpot graph. You see these are different representations of the lineage trees. On the left side, you see the spot graph. It shows the spot A that exists at time point 1, 2, and 3, and then splits into spot B and spot C. The time point B exists at time point 4 to 11, and spot C exists at time point 4 to 6. And you can translate that in a more generalized representation. It's called the BranchSpot graph. It reflects the lifetime of the spots, which in many cases will be cells, but yeah, since Mastodon can also be used for tracking other, can be anything which you can track in a time-lapse movie. And since there are 3 time points here, this translates into 3. The 8 time points here of this spot B, that translates to a duration of 8, and this translates to a duration of 3. The time edit distance that we can compute from this BranchSpot representation is quite related to the Levenstein distance that you may all know. So the Levenstein distance is used to compare the similarity of strings. So for example, the string Honda and the string Hyundai, they may have a Levenstein distance of 3, and that is because the Levenstein, or the concept of the Levenstein distance defines 3 allowed edit operations. That's adding a letter, it's removing a letter, and changing letters. So for example, if you want to change the string Honda to the string Hyundai, you would need to add a Y, you would need to change the O to U, and you would add to an I. And that's 3 of these edit operations. Each of these edit operations is associated with a cost of 1, which results in a Levenstein distance of 3. And quite similar, the concept of the tree edit distance works. So there's also allowed tree edit operations, which you can find in the documentation of the in the Java doc of the source code. So, and yeah, I will not go into too much detail here. So it's possible to change a label, it's possible to remove a subtree, it's possible to add new subtrees, and so on and so forth. And that's quite similar to these edit operations with the Levenstein distance, and also to these edit operation, there's associated costs. So for example, removing a subtree or adding a subtree, the cost could be the duration of those subtrees. I think it gets clearer with an example that I will show you now. So imagine these 2 trees, and the first tree, there's a branch spot which has a lifespan or a branch duration of 20 time points. Then there's a second branch spot which has a duration of 10, and the third one of 30. And here, that's this in the second tree, it's quite similar. So we have this 10 here as well for the branch spot 2, but for the branch spot 1, we have 30 instead of 20, and we have 20 instead of 30. So, and this would result in an edit distance of 20 because 2 nodes with a difference of 10 need to be changed in both scenarios. So this 20 and this 30 need to be changed, and this 30 and this 20 needs to be changed, and that's 10 each, and that sums up to edit distance of 20. And in a more complex example would be this one. There's this branch spot 13 and 12, so that's a difference of 1s. Then there are these branch spots which have a lifespan of 203 each, and here's 327 each, so that's a difference of 24 each. And there's 2 new branch spots which are added, which have a duration of 10 each, so that sums up to 1 plus 2 times 24 plus 2 times 10 equals 69. So that's the tree edit distance between these 2 trees. And Yeah, we use this tree edit distance to determine the similarity of the trees. The next thing that we do is that we take all of these trees, we generate a matrix from them, where in the matrix we compute from every tree to every other tree. So starting from the root cells, the tree edit distance. So, and that leads us to a tree similarity matrix. So you can see here, for example, this tree asymmetric 1 compared to itself. That's a tree at a distance of 0 because it's totally identical. And compared to asymmetric 2, it's a tree at a distance of 0.16, which is rather low, which is what we would expect because they are quite similar. But as you can also see, to the non-dividing one, it has a quite big difference. And also to the single division ones, this asymmetric ones tree, you can see here, it looks very dissimilar like these two trees. And so on and so forth. With all of these, we create this similarity matrix. And this similarity matrix we can then use to compute some hierarchical clustering. And yeah, for the hierarchical clustering, I will only explain very shortly here. I recommend that if you are interested in that, there are many resources in the internet that you can use to inform yourself. So the idea of the hierarchical clustering is that we take that we take the results of the similarity matrix and insert it at data points in such a two-dimensional data space. And then we try to find the closest one matching. So in this example, similar lineages would be this one, single division 0 and single division 1, since they have similarity only of 0.08. So they would form the first cluster. And this is what we can also see in the dendrogram of this classification. So they form a cluster at around 0.08. And also this symmetric one, they form a cluster already at 0.09 and so on and so forth. And then from the average, as you can see here in this animation, I will wait and the animation starts again. So from these first two data points, an average is computed, and then this point is taken to compute the distances to the remaining ones. And there are different methods how to compute this difference to the remaining ones. There's the so-called concept of the single distance. So that would be the closest ones of two clusters matching. Then there's the average, where you would compute the distances from every point to every other point, and then take the average of that. Or then there's the complete distance, and the complete distance would be that the furthest clusters are, or the data points which are furthest away from each other, that they are taken into account as a link criterion. And this is also one of the parameters that you can see here. So there's average linkage, single linkage, and complete linkage. So this basically defines which linkage target strategy for the hierarchical clustering is chosen. There are two more parameters that I have not yet talked about. One is you currently have no selection. That's the feature. It's currently here's only branch duration available. So that's the cost function that I mentioned earlier. So there are two more parameters in this lineage tree classification dialog that I have not yet introduced. One is the similarity measure. There's normalized Zhang tree at a distance, per BranchSpot Zhang tree at a distance, and Zhang tree at a distance. And I would like to introduce these three to you as well. So the tree edit distance, that's the edit distance I already showed to you. So that's this example. And this tree edit distance from our point of view has a disadvantage. And the disadvantage is that as you can see here, so this tree and this tree, they are similar to each other, and also this tree and this tree, they are similar to each other. And maybe you would even say they are to a degree similar to each other, but this is not reflected by the normal tree-edit distance, because here you have, here the sum tree-edit distance would reside in a lower tree-edit distance, since it is less points that are to be covered. And this is a higher tree-edit distance, since here are more points contained in this example. And so in order to compensate for the fact that trees that are similar just because they have more nodes are not considered so similar by the tree-edit distance, we came up with the possibility to select two measures that compensate for that fact. So the first is the per branch spot sum tree-edit distance that you can select here, and that per branch spot sum tree-edit distance, it does the following. So it takes these two trees which have a tree-edit distance of 49, as you can see here, and it divides that by the total number of branch spots included in the two trees. That results in a tree-edit distance of 8.2, and these values are a bit more independent of the actual sizes of the compared trees and reflect more the difference in the general pattern. And the second one, we call it the normalized sum tree-edit distance. It is available for selection in that dialog as well. So you have here the normalized, and it's given the one that we would recommend, but we left the other possibilities for you to experiment as well. And the same is also for the linkage strategy. We recommend the average linkage strategy, but you can also experiment with single linkage and complete linkage to see if it results in, or if you get good results for your use case with.
Okay, and with that, I would like to show the last new plugin of the Mastodon Deep Lineage 0.0.1 release. This plugin is the export label image using ellipsoids plugin. And the plugin is capable of exporting the ellipsoids that you can see here as a label image with no other data inside it. This may be handy if you want to run pipelines with the ellipsoids that you have computed inside Mastodon, inside other software. So in order to demonstrate this plugin, I have opened already this example dataset that you can find on this Mastodon repository, the tgmm-mini dataset. So here you can see the plugin dialog. You have three parameters that you can enter. The first parameter is the label ID. You can choose between spot track ID, branch spot ID, and spot ID. And this is related to the spot table. So as you can see here, there's the spot ID and also the spot track ID in this column. And these IDs, they relate to these ellipsoids that you can see in the big data view, and also to these branches that you can see in the branch view. And they will be used during the export as a label, as a value for the pixels that represent the ellipsoids in the label image. And the third option is the branch spot ID, and that's that ID taken from the branch spot data column. Okay, going back to the dialog, there's another parameter, that's the frame rate reduction. This frame rate reduction you can use to reduce the data that is exported. Sometimes this may be handy. In this case, I have set it to 1, so this will result in no change. But if I would set it to 2, this would mean that, as you can see here, there's in total 30 frames, and a frame rate reduction factor of 2 would mean that only every second frame is exported this plugin, so that would result in 50 frames only. And if you set it to 3, then it's only every third frame, and it would result, for example, in 10 frames then in the final result. This may sometimes be handy if it's an issue of the pipeline that you sequentially run with this exported data, where which may not be capable of handling big data. So that's the reason why this parameter is there. And the last parameter is the file path. So in the first example, I will export the image with the spot ID and also have named the file with that. So once you've clicked OK, you can see a progress bar in the Fiji main application showing the progress of the export. And once this is finished, I will export a second label image using the BranchSpot ID. So I will also call that file BranchSpot ID. Okay, I'm going to export it as well. And in order to show you that you can use this or in a different software, I will open Napari. So here we have Napari, and now I will import the dataset. First, I'm going to import the file with the spot ID. I'm going to the 3D view. So you can see here this data inside Napari, and we can also see that we can go through the time lapse. And you can also see that while we are going to the time lapse, the colors of the spots change every time. And that's because we have selected here the spot ID and the spot ID. So every spot has a different ID in a different time frame. And that's why these colors flicker all the time. And if I import, for example, the file with the BranchSpot ID instead, you can then see that the colors remain more constant over time. So they are actually only changed if there's a splitting event like here. Then a spot gets a new BranchSpot ID, but this happens only in these splitting events. So that means that each of these ellipsoid states has a constant ID over time, as you can see here.